So with Chapter 6, we're going to look at a lot of different specific polygons and talk about properties of each of those polygons. Specifically, quadrilaterals. We're going to have lots of quadrilaterals, and each quadrilateral is going to have their own set of properties that apply to that quadrilateral. So we're going to start that off with Section 2, where we're looking at the properties of parallelograms. And that's going to be our first term here. And by definition, a parallelogram is a quadrilateral with both pairs of opposite sides parallel. And so that's our definition. Now we're going to spend the whole section learning different properties of parallelograms, but if we want to say that something's true by the definition of parallelogram, we're just saying that opposite sides are parallel of a quadrilateral. And just as a reminder from Section 1, quadrilateral just means a four-sided polygon. And any quadrilateral, this is true not just for parallelograms, but in any quadrilateral, opposite sides do not share a vertex, and opposite angles do not share a side. And there's a nice little diagram here. We've got some sort of quadrilateral. It looks like it might be a parallelogram, but notice there's no markings on it. So unlike the picture above, where we see this top side is parallel to the bottom and the left side parallel to the right side, since we don't have those markings on this one quadrilateral below it, we don't necessarily know ABCD is a parallelogram. It looks like it, but without being told opposite sides are parallel, we've got some quadrilateral. But really what's important here is knowing how to identify opposite sides and opposite angles. So AB and CD would be considered opposite sides. They do not share a vertex. BC and AD, the top and bottom, would also be considered opposite sides. Angle A and angle C are opposite angles, as well as angle B and angle D. They don't share any common sides. Pretty intuitive, just kind of a word we want to make sure that we are familiar with so that when we use it to define some properties, we're all on the same page. So you can abbreviate parallelograms with just a little parallelogram symbol, and the book says or parallelograms, plural, if you to use the symbol and put an S in the middle. I've actually never seen that. I typically just draw myself a little symbol, and it's usually pretty ugly, but I make it work. See, just like that's pretty ugly. We'll try that again. Something like that. Just because we don't necessarily want to abbreviate parallelograms just to parallel, since that's a word in of itself, we use that little marking. So if we have a quadrilateral and it's a parallelogram, then we know opposite sides are congruent. So that's going to be our first property of parallelogram. So when we're looking at a parallelogram, opposite sides are congruent. So that was why we needed to determine what qualified as opposite sides. So notice here this parallelogram, ABCD is a parallelogram. It's got opposite sides marked parallel. Since we know it's a parallelogram, then we also know that those opposite sides are congruent. So AB is congruent to CD, and BC is congruent to AD. So that's the first property, and we'll take a look at using that here later on. Now, in addition to knowing what opposite sides are, we also have what we call consecutive angles. And angles of a parallelogram that share a side are called consecutive. So if we have a quadrilateral, meaning we've got four sides, our angles are either going to be opposite or they're going to be consecutive. Now if you get into larger polygons, a pentagon, a heptagon, and so on, you can have angles that are neither consecutive nor opposite. But in this case, consecutive angles are the angles that are not opposite each other, they share a side. So for example, angle A and angle D are consecutive angles. Notice here, B and C are also consecutive angles. Also, A and B are consecutive, and C and D are consecutive. So any two angles that share a side, they're next to each other. All right, now we're going to take a look at our next property for parallelograms. So again, we say if a quadrilateral is a parallelogram, then consecutive angles are supplementary. Now remember how I keep harping on those past vocab terms and making sure that you know them? Here's why. Supplementary means that they add up to 180 degrees. So we need to know the definition of that term in order to know what this theorem here, property tells us. So any parallelogram, its consecutive angles are going to add up to 180. So in this case, again, we've got parallelogram ABCD. A plus B would equal 180. B plus C would equal 180. C plus D would equal 180. And A plus D would equal 180. We'll have a theorem here in a minute that talks about what's true for opposite angles in a parallelogram. Here we're just looking at consecutive. So let's go ahead and try an example. We've got multiple choice going on, and we're asked, what is the measure of angle P in parallelogram PQRS? So again, let's talk about this parallelogram here. It's kind of the inside of my desk lamp, PQRS. Now notice there are no markings on that showing opposite sides parallel, but we're told it's a parallelogram with this little symbol here. So that's what's important about having this little parallelogram symbol. That's its way of telling us opposite sides are parallel, and that then we can apply these properties of parallelograms. So that last property we just talked about said consecutive angles are supplementary. So in this case, angle P and angle S share side PS, they are consecutive, so they are also supplementary. So, using that, we know by the definition of supplementary that angle P plus angle S should equal 180 degrees. So the measure of angle P plus the measure of angle S will give me 180 degrees. That's one of my properties of parallelograms. Now let's go ahead and use substitution. Since S is equal to 64 degrees, we're going to substitute. And then we get the measure of angle P plus 64 equals 180 degrees. I've got one equation, one variable, that's my angle P. So we can solve by subtracting 64 from both sides to get angle P by itself. And we get the measure of angle P is equal to 116 degrees. That's that first property of parallelograms that says, in a parallelogram, consecutive angles are supplementary. We can check that by saying, hey, angle P plus angle S should equal 180, well, 116 plus 64 does in fact equal 180, so we've checked our work and we're good. So consecutive angles are supplementary. Now our next property says if a quadrilateral is a parallelogram, then opposite angles are congruent. So our last property talked about what happens when we're looking at consecutive angles. This one talks about opposite angles. And remember, we defined opposite angles to be angles that do not share a common side. So opposite angles are congruent. So again, here I'm looking at parallelogram ABCD. In this case, angle B would be congruent to angle D, and angle A congruent to angle C. So we still have that same property in place. We're adding properties on top of each other. So now we know consecutive angles are supplementary and opposite angles are congruent. And there's a really nice proof in your book to show you how you can derive one property from the other if you're interested in that. So here we're asked to find the values in each parallelogram. Again, we're told we have a parallelogram, so even though we don't have those opposite side markings, our instructions tell us we're looking at a parallelogram. And that last property told us opposite angles are congruent. So in this case, this kind of upper left-hand angle is going to be congruent to the bottom right-hand angle. So they both have to equal 130 degrees, which means 6a plus 10 equals 130. One variable, one equation we can solve. Start by subtracting 10 from both sides. 6a is equal to 120, and then divide both sides. Oops, I missed my a in there. Let me try that again. Divide both sides by 6 to get the a by itself, and a is equal to 20. Again, go ahead and check that by plugging it back in. That top left-hand angle should equal 130 since opposite angles are congruent. 6 times 20 is 120, plus 10 is 130, so both angles there are 130. Let's look at one more practice problem working with opposite angles being congruent. Again, upper right, bottom left are opposite angles, and we know that they need to be congruent since our properties of parallelogram says opposite angles are congruent. In this case, unlike my last one, I don't know what they're going to equal, but I do know that they should equal each other. So 4a minus 4 needs to equal 2a plus 30. Solve for a, I'm going to start by subtracting 2a from both sides, so I get my a's all on the same side. 4a minus 2a is 2a. So 2a minus 4 equals 30. And I'm going to add 4 to both sides to isolate my variable. So 2a equals 34. And my last step is going to be divide both sides by 2. And 34 divided by 2 is 17. So in this case, I get a value of 17. So far, let's just recap the properties we've talked about. We know by definition, a parallelogram has opposite sides parallel. Our first property said opposite sides are also congruent. Our second property said consecutive angles are supplementary. And our third property said opposite angles are congruent. So already within the first half of our notes, we know 4 things about parallelograms. And we're about to learn a 5th. So our next property of parallelogram says if a quadrilateral is a parallelogram, then its diagonals bisect each other. So when we're looking at a parallelogram, diagonals bisect each other. A diagonal is any segment connecting non-consecutive vertices. So in this case, my diagonals connect my opposite vertices or my opposite angles. So here a diagonal would be BD and AC. Also, remember this term bisects. That comes back from, I believe, chapter 1 as well. Bisect is going to mean it cuts in half. So it takes that diagonal, for example, BD, drawn from opposite vertices, and cuts it in half. So notice here they put where my 2 diagonals intersect as point E, and BE is going to be the same length as ED, and then AE is the same length as EC. Now, pay close attention here. Notice the markings here. BE has 2 congruent markings. ED has 2 congruent markings. Those 2 are congruent. They are not congruent to AE and EC. So we're bisecting the diagonal, but we're not making 4 congruent segments. We're making 2 pairs of 2 congruent segments. So just kind of keep that in mind, that we're not making all congruent segments. Just the diagonal itself gets bisected. All right, so we're going to look at our next example, and this brings back some of our algebra terms, or some of our algebra, not terms, sorry, but algebra processes of solving systems of equations, meaning we're actually going to end up with 2 equations here with 2 variables, and we're going to need to use either substitution, elimination, or graphing to solve. All right, so let's look at what we have first. It says we're going to need to solve a system of linear equations. I just talked about that. To find the values x and y of parallelogram KLMN. So again, we're told it's a parallelogram, so I know I can apply those properties we've been talking about. And I'm asked to find KM and LN. So notice what we're given here. I'm not looking at angles, and I'm not looking at sides. I'm looking at the diagonals. So I'm going to go ahead and use that last theorem we talked about, or last property, theorem 6-6, that says that diagonals of a parallelogram bisect each other. That means that, I'll grab my highlighter, my diagonal, here's one of them, LN, is bisected at P, or P is the midpoint, meaning LP is equal to PN. And I've got another diagonal here. My other diagonal is KM, and the same property applies, that KP is equal to PM. Again, notice these are not 4 congruent segments. They're not all equal to each other. One diagonal is cut in half, the other is cut in half. So now let's use substitution, and let's replace what we know each of those segments to be equal to. So LP is just x. So x has to equal Pn, which is y plus 2. That's my first set of linear equations. The next, Kp is y plus 10, and that has to equal Pm, which is 2x minus 8. Now, I've got 2 equations and 2 variables, so I can solve, but I'm going to have to use one of my tools of how to solve systems of linear equations. As I mentioned, we can use substitution, elimination, and graphing. I'm going to go ahead and choose substitution since it's not set up nicely for an elimination process. And I could graph, but I'd have to solve both for y, and that would probably take me a little bit more time than substitution. There are lots of right ways to do substitution, so if you approach this differently than I do, that's okay. the way I'm going to do it, since I already have one equation solved for x, I'm going to use substitution into my second equation, take out the x, and replace y plus 2. So I'm going to use substitution to solve. Now you are perfectly welcome to solve for y instead of x, or to solve the second equation for a different variable. There are, again, lots of great ways to approach this. I'm just going to try and do it what I think will be the most streamlined and fastest approach. So I'm taking my second equation, y plus 10 equals 2, and I'm replacing x with y plus 2 because my first equation says x equals y plus 2. And make sure you use those parentheses. If you leave out the parentheses, you're going to forget to distribute that 2 to everything that is in that equation. So make sure we leave that as a distribution problem. Now I'm just going to go ahead and start simplifying so I can get to a point where I'm comfortable. I'm going to leave the left side as y plus 10, and on the right I'm going to distribute the 2. So I get 2y plus 4, and then I've still got that minus 8. Again, I'm going to leave the left side. I'm going to combine like terms on the right. So I have 2y, and then 4 minus 8 gives me a negative 4. Now this is probably at a point where you're comfortable with. We've done this quite a bit in this class. I have a variable on both sides, so I'm going to start by subtracting y from both sides to get my variables all together, and they cancel on the left, so I got 10 equals 2y minus y is just y minus 4. And then I'm going to add 4 to both sides to get that y out by itself. So I get 14 is equal to y. I'm partway done with what I need. But I don't just need y, I also need x in order to get to my end goal of finding km and ln. Well, if we go back up here to these equations we set up in the beginning, notice x is just equal to the y plus 2. So I'm going to find x by substituting in 14 for y, since we just found y is equal to 14, and adding 2. So x then is equal to 16. That's the second part of my equation. Now I'm not quite done. I don't just want to know what y and x are. I actually want to know the lengths of km and ln. So km, let's go back up to my picture, is going to be equal to y plus 10, that's kp, plus pm, which is 2x minus 8. So I'm just going to add all those together, and I'm going to replace what I know. Y is 14 plus 10 plus 2 times 16 minus 8. So let's go ahead and just throw that in our calculator here. Oops. Trying to get it so I can see them both. There we go. So 14 plus 10 plus 2 times 16 is 32 minus 8. My km is equal to 48 units long. And last, we want to find the length of ln. ln is just going to be LP plus PN. So I take my x value, which is 16, plus my y value, which is 14, plus 2. 16 plus 14 is going to give me a value of 30, plus 2 is 32. So that's a little bit longer process that we're used to doing, but that whole first part was really just a refresher from that Algebra 1 solving systems of equations. So when you have 2 equations and 2 variables, make sure that you use that process to solve for each variable, plug it back in to find the other variable, and then always make sure you're answering what they're asking for. In this case, it was finding the lengths of each diagonal. All right, so our last property, it pulls off of some properties of parallelograms, but we're not actually looking at parallelograms in this case. We're told if we're given 3 or more parallel lines, if 3 or more parallel lines cut off congruent segments on one transversal, then they cut off congruent segments on every transversal. So that's kind of a confusing wording, I feel like, but really all they're saying here is if I have parallel lines and they're evenly split with one transversal, they're going to be evenly split with any transversal. So if we look at our picture here, I know these 3 lines that are horizontal are parallel. They're marked here with these little arrows that show me they're parallel. Then I also know I have this transversal here, AE, and I'm told that it's cut equally, meaning AC is the same length as CE. That's all given to me. If I have this sort of situation where I have 3 or more parallel lines and a transversal that's cut evenly, any other transversal will also be cut evenly. Meaning, I've also got this transversal here, BF, and it has to be cut into even pieces, meaning BD has to be congruent to DF. Now, be aware, I'm not saying every segment is congruent. My segments in the left transversal are not congruent to the segments in the right transversal. All I'm saying is that the segments created by that second transversal are also congruent to each other. So let's go ahead and put that into play and practice a problem using that property. So we have a new figure here at the right, and we're told AE parallel to BF, parallel CG, parallel DH. So all 4 of those vertical lines there are parallel. And I'm also told that the length of AB is equal to the length of BC, which is equal to the length of CD, meaning this one is congruent to this one, congruent to this one, and they're all 2 units long. So I've set this up, or this is set up, just like the beginning of that last theorem. If parallel lines are cut evenly by a transversal, then they're going to be cut evenly by all transversals. So notice here I have another transversal, and that's EH. Since AD was cut evenly by these parallel lines, I also know then that EH is cut into even pieces, meaning EF is the same length as FG, and it's the same length as GH. So since AB is equal to BC equal to CD, using that previous theorem, we know EF has to be equal to FG, has to be equal to GH. Now, not all 6 of those are equal to each other, but they're equal to the pieces made by their own parallel segments. Now, let's finish this problem. We're also told that EF is equal to 2.25. And I'm asked to find EH, and EH is actually from this first parallel line to the last parallel line. Well, since EF is 2.25, and EF and FG and GH are all congruent, all 3 of those segments have a length of 2.25. Oops, I missed a 2 on that one. So, if I want to find EH, that's just going to be the sum of each of those 3 segments. So that's going to be EF plus FG plus GH, and each of those segments is 2.25. So it's really just going to be 3 times 2.25, or 2.25 added together 3 times, which gives us a total length of 6.75. So again, once you've got parallel lines, cutting one transversal into even segments, you're going to cut all transversals into even segments. So let's look at one more example. We're going to use the same figure, so I'm going to go ahead and erase the markings I put on it. So we're going to take the same figure, but we're going to give it some different circumstances. So it asks us to use that figure in problem 4, the one right up here on the right. And if I know EF is equal in length to FG, equal length to GH, and they're all 6, so all 3 are 6, and if I know from A to D it's 15 units long, what is the length of CD? So a couple things going on here. Still got my parallel lines, and now I've got a different transversal to start with, but that transversal is cut into even segments. So I'm going to use that property to tell me that all transversals are going to be cut into even segments. So since EF is equal to FG equal to GH, then I can say AB is equal to BC equal to CD. Okay. That's using that property we just talked about. The other thing I know is that AD, or 15, since AD is equal to 15, is going to be equal to all 3 of those segments added together. So 15 is equal to AB plus BC plus CD. Now, if we use substitution, let me try that again. And I replace AB and BD with CD since they're all congruent. I get 15 is equal to CD plus CD plus CD, just replacing each congruent segment with CD. Now, CD is just one variable. I'm going to rewrite that as 15 is equal to 3 times CD, since adding CD 3 times is the same thing as 3 CD. And solve for CD by dividing both sides by 3. And I get 5 is equal to CD. AB would also be 5 then, and BC would be 5 as well. So, started out talking about parallelograms. By definition, parallelograms have opposite sides parallel. We learned that opposite sides are also congruent, opposite angles are congruent, and consecutive angles are supplementary. Definitely have this written down, have these notes somewhere. We're going to just keep adding more types of quadrilaterals and more properties about them. So don't just try and breeze through this and listen and call it good. Definitely write these down because we're just going to keep adding to it. If you have any questions, let me know. Otherwise, thanks for watching.